Hi, I'm Ray Sheen. Well, we're now going to talk about the ANOVA test. This test has become strongly linked to Lean Six Sigma because it's used on many of the advanced Lean Six Sigma analyses.
Again, we start with a hypothesis testing decision tree. We've discrete and continuous X and Y data, normal data, and multiple variables. That gets us to ANOVA. Just to be clear, we could use the ANOVA test with two variables, but the t-test is much simpler from the mathematical standpoint. However, since we are letting the computer do the math, there's nothing wrong with using an ANOVA test with just two samples. So let's look at the one-way ANOVA. ANOVA stands for Analysis of Variance, a bit of a misnomer because it uses both the means and the variance in the analysis. It compares the means from each of the samples in the analysis to determine if one of the means is statistically different from the others. In this regard, it's similar to the two-sample t-test, but instead of just two samples, it can have many samples. It's often used to identify significant subsets of the data in a large population. That is a feature behind its use in both the gauge R&R analysis and the design of experiments analysis. It can sort through the many data points based upon the categories being used and determine which, if any, provides a result that is statistically different from the others. So the null hypothesis is that the mean of all the subsets is the same. There's nothing to see here. And of course, the alternative hypothesis is that at least one of these subsets is significantly different from the others. You may be wondering why we would use ANOVA when we could do the same thing with t-tests. Well, the problem is that you can't get the same fidelity in the answer by using multiple t-tests. Keep in mind that with our normal Lean Six Sigma confidence level of 0.95, there's still a 5% chance for a type 1 error, a false positive. If we had 4 samples, we would need to conduct 6 t-tests, so the probability of a type 1 error is compounded. That means that our chance of making a type 1 error across all 6 tests is now up to 26.5%. And keep in mind that the type 2 error probability is often higher than the type 1 error, so the chance of a type 2 error is even higher. The more t-tests we run, the more likely we are to make a wrong decision. However, with ANOVA, it's only one test that needs to be run, and that will check all of the relationships between the sample means. In addition to that, ANOVA is somewhat forgiving on the assumption of normal data. It will tolerate a low level of non-normality and still provide excellent results. Let's spend another minute on the ANOVA approach. The ANOVA analysis will determine if the between-group variation is large enough to distinguish a difference from the within-group variation. Now, the between-group variation is a variation of the different subset means. The within-group variation, this is where variance comes into play, is based upon the variance that is occurring within the entire group itself. ANOVA will calculate an F statistic, which is the ratio of the between-group mean sum of squares over the within-group mean sum of squares. Another feature of ANOVA is that it does this calculation assuming that the sample sizes in the group are not the same. The formula for each of these mean sum of squares is shown here. Note that the between group mean sum of squares is comparing sample means to the grand mean of all the data, while within group mean sum of squares is looking at the variation in each unique sample and then summing those results. A quick word about the sum of squares. The F statistic can also be expressed as the sum of squares of the treatment plus the sum of squares of the residuals. The sum of squares of the treatment is another way of expressing the between variance. You can see the equation here. And the sum of squares of the residual error is another way of expressing the within variance. It's based upon the residuals of each of the data points. We can then convert these sum of square values into mean square values when we divide by the appropriate number of degrees of freedom. This is tied to the number of samples that we are working with. The ratio indicates the magnitude of these effects compared with the inherent variability. The larger the magnitude, the larger the effect. If the magnitude of the ratio is small, it implies that whatever variation we see from sample to sample, well, that's just based upon chance, because all the variation is still within the predicted interval for variation.
ANOVA is a great test for many applications within Lean Six Sigma. And in particular, it's well suited for sorting out a very complex situation.